Morning everyone. So we're going to do a quick tutorial on introducing how to deal with problems that involve two or more bodies, two or more masses. Those situations could include the one I've shown here where I have a block A right here pushing on block B. We will also eventually look at situations where you have a string between two bodies and the string is pulling one while gravity might pull the other, or you might have two strings. So the third law of motion plays a critical role in understanding this. And we're going to also introduce, even though I'm not going to go into great detail in terms of the notes, the idea of external and internal forces. So pay close attention to this particular problem and then come in with questions, and hopefully we can work things out so that when we move on to the other applications, then it will be pretty straightforward. So the key to doing these, just real quickly, is that we want to isolate each body and draw separate diagrams. Okay, so each object has its own force diagram. So when we go to apply the second law, we can make a choice which body do we want to apply to, and we'll see we also have a choice of doing it for the whole. Okay, so each force diagram is the forces are independent of the other body, and we also want to pay careful attention to action and reaction forces. Okay, that's where the third law comes into play. Okay, we're going to apply the second law to each body, all right, and we'll talk about this, or you can apply it to the whole system. So let's do a quick one. All right, so let's say I have two blocks, A and B, and there's a force being applied to them by somebody or something. We don't know what it is, but what's critical about this F is that it's external to A and B. It's not part of A and B. Okay, and you're told that it's 12 newtons, so I'll label this as 12 newtons here. And we know that box A has a mass of 3 kilograms, and box B has twice the mass, so I'll just put in 6 kilograms. And what we want to know are a few things. We can ask, well, what's going to be the acceleration of the system? What's the acceleration of box A? What's the acceleration of box B? We could talk about how much force does A apply to B, etc. So in order to understand this, we're going to do a force diagram where we're going to isolate A and B. So pay close attention to this. So first off, we know that and we're going to focus on horizontal here. We're not going to focus on the verticals because it's just going to be normal force and it's going to be gravity. Okay, so I'm going to put the 12 newtons there. Let's continue on looking at A. So this is a frictionless situation, so there's no friction. Ask yourself right now, is there another force acting on A? Okay, now there is. And where is that force coming from? It's coming from B. B is pushing on A. Now, why is that? Well, there's two ways you can approach it. I'm going to take a slightly different approach. I'm going to come around to it in a second. We understand that if I push on A has to move. A is pushing on B, which causes B to move. So understand that F is not directly acting on body B. A is acting on B. So I'm going to go over to B, and I'm going to put an arrow here, and I'm going to call that FBA. That's the force on B due to A. Okay, it's not this original F, okay, but it's B on A. So if B pushes on A by the third law of motion, A must push on B. So I'm going to call that, let me say that again. B must push on A. So the force on A due to B is the action-reaction force from A on B. So, hopefully that makes sense. Now, let's look at, and there's no other forces acting on A, at least in the horizontal direction. So let's focus on B. We already established that the box A is pushing B. We've got that. There's no opposing force over here because there's no friction. So we're done. You might say, well, wait, where's the paired forces? So shouldn't we have even number of forces? Here are one pair, action-reaction. Okay, where is the other pair? Well, it's there, it's just not relevant. So here's my action-reaction. There's a force from here from some object, so the third law says that A has to be pushing the other object back. We don't know what that is, but it's not relevant because it's not part of our system, so I'm going to ignore that force. Okay, so now we can write an expression of the second law for each body. It should be pretty straightforward. So if I focus on body A, right? I see I have two forces right here. So I'm going to say F net. I'm going to say A of body A is the force F minus the force from on A due to B, there's my net force, divided by M. So what M are we talking about here? Well, since we've isolated body A, we're just going to put the M of A. Okay? That's the idea of a free body diagram. We don't have to, I just want to get rid of that circle. Okay, so by the same reasoning, we're going to have the same thing for B. Okay, so on B, there's only this force, so the net force is just force of B on A divided by the mass of B, because the force diagram is for B only. Third choice we have is that the acceleration, so this is A of B, is A of the A and B, I'm just going to call it the system, is equal to the net force due to all three, right? I look at all 1, 2, 3 forces there, and what I see, that would be F minus FAB plus FBA, okay? Because BA is in the same direction as F. And that's going to be divided by the mass of A plus B, because now I'm using both masses and all the forces on both masses. And if you pay attention, you see that because of the action-reaction, because our system includes this, these are going to cancel. So action-reaction forces cancel when our system includes the two bodies. If we isolate the two bodies independent of each other, then they're not going to cancel. And that's a lesson we learned from the third law. So in other words, it's just going to be F over MA plus MB. Okay, so notice two important outcomes of these three applications. For individual masses, namely this one and this one, there are two unknowns. Okay, in other words, in this equation right here, I don't know the acceleration, I want to find it, and I don't know this value. So to solve this in of itself is not, you can't do it. And the same thing with this one. I don't know A and I don't know FBA. So it makes it difficult. Now, hopefully you understand that this acceleration and this acceleration have to be the same because they're moving together. So I have two equations and two unknowns, and then I could do it that way. But there's an easier way of doing it. The easier way of doing it is for the system, so the easier way of doing it is just solving the acceleration based on this equation, because I know F, that was given, we know the individual masses, and I can solve for the acceleration of the system. And again, sorry for the messiness of everything here. Let me just kind of erase all this. Okay, let me just put the F, A, B, F, B, A. Okay, is that these two have to accelerate together. So the acceleration of A and B has to be the same as the individuals, otherwise they would separate, which doesn't make sense. And I already talked about this. The other thing to note is that for the system, when you include all the bodies, in this case two objects, the action-reaction forces cancel. And that makes it a lot easier to work with. Okay, so let's put in some numbers here and apply it. So how does the 10 Newton force applied to F compare to the force A pushes on B? In other words, if this is 12, okay, what is this value here? Common sense would say that's going to be 12 as well. But if you apply the second law appropriately, it can't be 12. Because if the 12 is pushing both objects, and this force is only pushing B, and we have to get the same acceleration, this force has to be a fraction of the 12. So we're going to work it out formally before I give you any shortcut. Okay? So it is how does the force F compare to the force? That F is greater than the force on B, the force on B, due to A. So let's show why. Okay, let's calculate that ratio. Okay, so what I'm going to do, and this is the long way of doing it, but I think you can understand, I'm going to figure out the acceleration of the system first. So I'm going to say A of the system is equal to, and this is coming from above, F divided by the sum of the two masses. That's from this equation right there. Okay, so that's 12 divided by 3 plus 6, which is 9, which is going to be 1.33 meters per second squared. So why did I do that? Because now I'm trying to solve for FBA. I don't know this. So where does that show up in my equations? It shows up in this equation here. Well, now I know the acceleration of the system. So I can say, so this is the second part, I can say A, I'm just going to call it generic A now because all the A's are going to be the same as FBA all over M. So I'm going to say FBA, F on B due to A is equal to M. Now this is important. I got to be careful. It's the M of B. So it's the mass of B times the acceleration of the system. So that's going to be 6 times 1.33. I'm not going to put units in. So 6 times 1.33 is 8. I think I did that right. 1/3 of 6 is 2. 2 times plus, yeah, so that's 8 newtons. Okay, so what I see, and if I kind of erase all this, let me just start afresh. If this is 12, this 12 newtons is pushing, even though it's acting directly on A, because A is pushing B, it's pushing this entire mass of 9 kilograms. Okay, but B is being pushed by A. And since B has a smaller mass than the system, it gets a proportionally smaller fraction of it, and we just found out that this is 8 newtons. Okay, now if this is 8 newtons, then the force on this must be 8 newtons as well by the second law. And look at that. Now let's look at A. We already know the acceleration of A has to be the same as the whole system. It should be 1.33. Let me show you I can get that using the equation that I just erased. In fact, let me unerase that. It's just so messy here. Okay, so if I apply this equation right here, what I'll see is A of A is the net force. Well, the net force is going to be the 12 minus the 8 divided by the mass. The mass is 3. 12 minus 8 is 4. 4 divided by 3 is 1.33. So I see that the net force on this has to be 4. The net force on this has to be 8. And to give the same accelerations, the net forces on each have to be different because their masses are different. Okay, so shortcut. How can I find the force on the second box? In this case, box B. The shortcut for this is the force on the second box, this is the force on B due to A, can be reduced to, it's a fraction of the original push. And it's really just the mass of B divided by the mass of A plus B. In other words, what fraction of mass does B have to the whole times the original applied force. Okay, so in this particular case, the mass of B was 6. The overall mass is 6 plus 3, and the original force was 12. So 6 divided by 6 plus 3 is 6/9 is 2/3. 2/3 of 12 is 8 newtons. And so that's a shortcut. But if this confuses you, don't remember that, this is the way to go. Figure out the acceleration of the system, understand that the acceleration of the system is the same as the acceleration of the individuals, then apply the second law to the individuals. Then I could also ask, well, how can I directly get the net force on A without calculating acceleration first? I can use the same equation. I can say the net F of A is simply the mass of A divided by the total mass times the original force. And we already saw that before. Mass of A is 3. 3 divided by 9 is 1/3. 1/3 of 12 is 4 newtons, and I showed that above. Okay, I know that's a lot to absorb, but if you go through this carefully again, it should start making sense. The key lesson is when you have two bodies, the action-reaction forces cancel for the system, but they don't cancel for the individual ones. And so when you go to figure something else, you just got to choose, does it make sense to solve for the system or to solve for the individuals? And depending on what's being asked, you got to do one or the other.